So good morning. Welcome to the Nobel lecture this morning. And it is my great honor to welcome Professor Haldane on behalf of the Hong Kong Physical Society, the Physics Department, HKUST, and also the Institute for Advanced Study of HKUST. I think it's one of those unusual and probably embarrassing situations when usually a host introduces a speaker. It is because you may not know the speaker, and therefore the host need to introduce the speaker. But these are one of the rare occasions that most of you don't know who I am, but everybody knows who is Professor Haldane. And so because of that, I can be very brief. And I'm sure that all of you know that Professor Haldane has won the Nobel Prize in 2016. But before that, he's already won a long list of prizes and medals. In fact, I have done my homework. I did it. This is a whole page. But I'm not going to read all of them to you. And just to say that he won all the prizes, including the very prestigious APS Buckley Prize, Dirac medals, etc., 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 etc. So, and then without further ado, let us welcome Professor Haldane. And let's, OK.
So this talk is part of it. The first part of it comes from a public lecture talk about Einstein and entanglement, and attached to it is stuff about the work that started some of this topological matter explosion that's happened in the last few years. It took a long time to take off, and I'll go into a little bit about its early history and connection with entanglement. So usually in public lectures, when people talk about quantum mechanics, they talk about the uncertainty principle, and that's probably as far as you ever get with any public talk anyway. But actually, if you look at the important things in quantum mechanics, it's now becoming clear that in some sense, the entanglement properties that Einstein pointed out initially is perhaps even more fundamental than the uncertainty principle, in the sense that it's really intrinsic to the way quantum mechanics works. So as I say, the two other things which are important, I guess, are the Pauli exclusion principle, which basically explains why you don't fall through the floor, because the electrons in your shoe doesn't want to be in the same place as the electrons bound to the atoms in the floor, and entanglement. So the entanglement was actually first pointed out way back in 1935 by Einstein and two co-workers at the other Institute for Advanced Study, the one in Princeton. And it was really an attempt to shoot down quantum mechanics. Okay, so Einstein did so many things that he's known for. And if we go through this list, of course, there's the famous statement that he made that what we now think is probably the cosmological constant is probably the vacuum energy and probably the dark energy. But he thought at the time adding the cosmological constant to his equations to try to make a steady state universe was his biggest mistake. And now, because we now think it's got everything to do with dark energy, it's an incredibly good mistake. And the other great mistake I would say he made was actually Einstein-Podolsky-Rosen Paradox, because his mistake was that he thought this was going to shoot down quantum mechanics. But it's turning out to be just as important a mistake for the advancement of science as the first one. As I say, so Einstein in the later part of his career devoted his time partly to trying to shoot down quantum mechanics. Because at some point in the 30s, before, of course, he got his Nobel Prize for quantum mechanics for the photoelectric effect. But later on, he turned against quantum mechanics, and he thought this entanglement properties it predicted, where you could do a measurement, two things could be entangled, and you could do a measurement on one and apparently instantaneously affect the other thing, was a kind of violation of relativity. And he called it spooky action at a distance, or called it in German spukhafte Fernwirkung, apparently. But Schrödinger came up with a better name for this thing. He called it entanglement, so that's where the thing comes from. And as I say, quantum mechanics has always been a pretty mysterious thing for the general public. It's actually more mysterious than relativity in many ways for them. But it's also really, for me at least, and for most practical physicists, it's also mysterious. But we get around that by actually working with it and not worrying too much about philosophical issues. Oops, and of course, we know on a practical level, no one lost their job by betting against quantum mechanics, betting for quantum mechanics, rather. And let's get the thing right. And for all its mysteriousness, it's the true description of the world around us on the scale which is removed from our immediate intuition on the human scale. But originally, the objections Einstein brought up of its entanglement property seemed almost like a philosophical issue. Right? It's something that philosophers were discussing along with questions, is quantum mechanics compatible with free will? Now, these are probably very useful discussions to have in a philosophy school, but they don't get you anywhere as a physicist. So practical physicists didn't pay any attention to this kind of stuff. But actually, in the last few years, it started to re-emerge that entanglement is not just some kind of philosophical issue in quantum mechanics. It's actually practical, and now we believe it's possibly the fuel that's going to drive maybe the quantum information processes of the future. And in condensed matter, one suddenly realized it's actually got a very, very useful for analyzing things. We now have entanglement spectrum and all kinds of things like this, which we can actually use to diagnose states of matter. So suddenly, probably I hadn't really ever thought much about entanglement more than 10 years ago. Maybe it started to come in when the density function or density matrix renormalization groups techniques came in, and eventually realized those were working on entanglement. But entanglement has now become a practical thing rather than just a philosophical thing. So, of course, the essential model for the entangled state is just the chemical bond, where the Pauli principle requires that if you have two electrons in the same kind of spatial state, they've got to be something different about them. And so if you put an upspin electron in, the other electron to fit in, and with the Pauli principle has to be downspin. But of course, you could do it any way you want. There's nothing special about up or down. You could take sideways, right to left, or at 90 degrees. So any two directions could be chosen, and the basic thing is that the quantum state, the entangled quantum state, the ideal one is this singlet, which is two things in whatever opposite state they are. And then this, of course, gave rise to the issues about, well, if you measure one electron's polarization in one direction, the other one will automatically be in the other direction. And of course, from a chemical bond on the scale of 1/10 of a nanometer, this thing is, of course, quite a robust thing, and there's nothing immediately surprising about it. Okay, it's quantum mechanics on the chemical energy scale. And of course, in this case, right, there's a protection of the thing due to energetics. But Einstein got worried about the issue about what happens if this state got expanded. Instead of being 1/10 of a nanometer where you made it a meter or a light year or whatever. And then he felt that the properties of this state on such a scale were just so ridiculous viewed from the common sense viewpoint that it had to be an incorrect prediction of quantum mechanics, and something has to go wrong somewhere along this line of expansion. And of course, when the two electrons are close together, their entanglement is protected by the energetic consideration that wants them both to be in that same state. And so the chemical binding energy essentially protects the entanglement on the chemical bond scale. But of course, when they're far apart, this entangled state becomes extremely fragile. And of course, the basic problem in using entanglement is to avoid the fact that if I made such a state where they were so far apart, any interaction with the environment, like another electron nearby here, would disturb this state, and it would still want to form a short-range entangled state with the new electron. So this, of course, is a decoherence process that has to be fought against if you're trying to do something with these entanglement properties for quantum computing. And at least one of the dreams of quantum computing, one that Microsoft is sticking about $1 billion into right now, I believe, is to use topological states to topologically protect the information against decoherence. Now, there's other schemes too. Google are putting their money into transmon qubits, a different scheme, and there's lots of different platforms for attempting to make store quantum information that various groups are proposing. But at least one of them has been fueled by the dream of what comes out of this topological states of matter. So the EPR experiment, well, he thought of making an EPR pair, which is taking a pair of particles in a box, this short-range entangled pair, this electron and two electrons in some kind of singlet state, or in fact nowadays photons. And then you switch the wall of the box off, and these two things take off in opposite directions. Now, the conservation of momentum guarantees that the sum of the two momenta has got to be about 0, because it was confined in that box to begin with. And so you've got these two things heading off in two directions, and if nothing hits them along the way, then they remain entangled, but they keep on going, and they have this long-range entanglement. And his problem was that if you made a measurement of the spin of one of these things, it would immediately imply that the spin of the other one was in the opposite direction. Now, the whole issue of free will comes in, because the experimentalist had to make a choice about which direction he was going to put his polarizer in. And then there's a whole issues about, you've got many worlds interpretation of quantum mechanics, coherent histories interpretation, consistent history interpretation, all these various things. And then there's a question, was the experimentalist actually exercising free will, or was it preordained he was going to choose a particular thing? Lots of these deep philosophical questions come in, but as I say, I don't worry about measurement theory personally. And so this was the basic EPR proposal. And Einstein thought it was just totally crazy that the measurement that he thought that the spin of the electron or the particle had to be known when they split up. So how could it be affected by this decision that was being made later? And his famous quote on that is that God doesn't play dice. And as I say, there was a whole issue of free will coming into the experiment, bringing the experimenter into the whole equation. But this problem got analyzed more deeply. In fact, in the years after Einstein's death, like David Bohm started off, but John Bell made a deeper analysis of EPR and quantum mechanics, and came up with even more refined tests. And of course, as I said, no one ever lost their job by betting in favor of quantum mechanics, because when the experiments were done by, I guess, Alan Aspect claims to be the first to have done this Bell experiment, the quantum mechanics comes out with like a 100% grade, right? 100% correct, and Einstein didn't live long enough to see that. And of course, in the modern terms, this is done not with particles and electrons with spin, but with polarized light, and then you have to choose whether you measure circular polarization or linear polarization. And of course, this is now entangled photon states have been created across oceans with modern optical fibers, which propagate so well, and it's going to be done in space. Probably have some entanglement between things at the 2L points, or such proposals are being proposed, at least for space experiments. But there's no doubt that entanglement does exist. If you can manage to protect things, you can make the entangled states apparently as far away as you can. Okay. So the era of discovering what cool things can be done with quantum mechanics is really only beginning. So I think there's a whole new couple of decades, which you might call the second revolution in quantum mechanics, ahead of us. We're now starting really to tweak quantum states and play with them in a very constructive way, rather than just bashing things with a hammer and seeing what flies out, right? So I don't know how successful we'll be in getting a quantum computer. People seem to be getting more and more confident every day. I'm certainly very impressed by how much progress is being made in prolonging coherence times, and So I believe we'll certainly get some kind of new technologies coming out of this, probably not in the too distant future. Okay. So of course, there we come to the thing about classical and quantum information. Classical information is just an on-off switch, 1 or 0, which you can think of as a lot of objects. A simple switch might be a large number of spins pointing up or a large number of spins pointing down, a lump of a ferromagnet or something. And the quantum information, of course, is stored in a much more delicate way in not as an up-down number, but in fact, for the simplest case, a spin-half object or a qubit. It's parameterized by a sphere. The states of a two-state system can be parameterized as the surface of the Bloch sphere, and you now have the information stored in this much larger amount of, much finer kind of way than just on-off. Okay. So what about topological quantum matter? So to the best of our knowledge, the basic laws of quantum mechanics have been known since about 1930. But I think an important point is just because we know what the laws are is equivalent to like the student here who has Maxwell's equation written on his T-shirt. Just having Maxwell's equation, knowing the laws of Maxwell's equation, you can summarize it in these four equations, but to actually go from just knowing those equations to understanding all the kind of neat things that can be done with electromagnetism has taken a long time. In fact, it's only in recent years that we've learned that we can make so-called photonic crystals, where we can manipulate the flow of light in interesting ways by introducing gaps in the frequencies which they can transmit at, and things like negative refraction index materials, cloaking, all kinds of things. So in fact, even electromagnetism is undergoing a change. And in fact, one of the things I'll talk about is there's actually now topological photonic crystals and lots of new things. So things have moved on, and just because one knew the laws of electromagnetism, we didn't know what happened. We didn't know what they allowed to happen. Okay. So as I say, before about 1980, the topological quantum matter was completely unknown. We had kind of no idea there was such a thing. And about that time, there were some new states of matter. I think I'd done something to the screen. Can someone come in quickly? I touched it, and it's a touch screen, so I made it bigger. Ah, good. Thank you. It's still missing at the bottom, right? It's now showing it not in single page mode. I'm not used to Windows machines, I'm afraid.
Anyone who knows system.
Ah, okay. Thank you. Keep my fingers off a Windows screen. I guess Mac hasn't got around to touch screens yet. Okay, so good. Okay, good. So okay, there was my point. So as I say, these things were quite unexpected, although in fact they're perfectly consistent with the equations of quantum mechanics. So in some sense, what you can do with either electromagnetism or quantum mechanics is a question of imagination, right? If you didn't even imagine something like photonic crystals, play. Do you want to stop it and restart it? Yeah. Okay, I'll skip through to where I was. Okay. I think I was somewhere coming up. Ah, what? You touched something. Don't touch it. No, it's not right. You've got to restart it now, or do whatever you do to kind of get it to the. Probably. No. Yeah, okay, good. Right. Okay. Oops. So I say before 1980, we didn't know about topological matter. And what actually happened around then, at least two apparently unrelated places, we started finding new states of matter with really surprising and unexpected properties. And it took quite a bit of time to really understand why these things were different. And the essential answer is that we now know that we can classify the states of matter by in a topological way. And all the previously known states of matter were topologically trivial. So we had no idea there were topologically distinct states of matter. And it's rather not surprising that they behave in different ways that we weren't used to. And hence, we were surprised. So now in recent years, there's been a lot of work in classifying this. And we've actually realized that these apparently different kinds of behaviors are all part of a unified picture, which is now emerged of topological states of matter. So as I say, in 1980, people were pretty confident, really. There was a classification, Landau theory of transitions. People thought they had a basic understanding of much of condensed matter. And suddenly these new things showed up. And in some sense, the metaphor is the tip of the iceberg, right? Because the two things I'll talk about, which both got kind of mentioned in the Nobel citations, well, of course, the quantum Hall effect itself already got 2 Nobel Prizes. But the topological aspects were mentioned. And there's also this apparently kind of obscure thing about spin chains that got mentioned too. But actually, below this whole surface of these two little things initially sticking up, there was a whole world of remarkable topological states which have been discovered and found, particularly in the last decade. So topological matter differs from ordinary matter because it's got some kind of properties, which essentially are entanglement properties, that can be described by whole numbers, like 1, -1, 3, 5. Well, the ordinary matter is described by kind of boring, trivial numbers, either 0, if we're counting 1, 2, if they're integers, or it could be even plus or minus, or 1 and -1, where 1 is trivial and -1 is not, which is the other kind of topology. But the thing is that states of matter, which are classified by whole numbers, can't continuously change from one to the other without something kind of violent happening. And the other thing, which is a kind of general principle, is there's almost always something interesting on the boundary between the two different topological states of matter. So if I have here a cartoon of a region of -2 matter surrounded in a background of 0 matter, there's got to be some place where 0 changes to -2, and what we typically find is something interesting happens at that boundary, because that boundary cannot go away. I can shrink or expand the -2 region, or cut it into 2 bits, but there'll always be a boundary between the two. So if we look at the kind of the kind of old-style classification of matter, which was based on broken symmetries, we have things like conventional solid order, which are crystals, where we have some kind of very regular array of particles or spins or whatever inside the material that are kind of different from the behavior in the vacuum, which doesn't have that array, or 2 different types of condensed matter. But there's nothing fundamentally special at the edges between the different kinds of ordered matter, and you can tell their difference by staring at the matter, the bulk part of the matter. Well, in at least some of the topological states of matter, for example, the quantum Hall electron liquid, there's actually no broken symmetry of any kind inside the material that makes it different from the normal material outside it. So the whole symmetry classification, partly systematized by Landau, doesn't tell you there's any difference between the quantum Hall liquid states and the vacuum or normal liquid states or whatever outside that system. But they are different. And that shows up that if I look at the boundary between the topologically ordered liquid state and the normal state outside, there is something very interesting in the quantum Hall case, which is a two-dimensional system that lives on a sheet. Then you have a one-way propagation of energy or information around the boundary. It was very unexpected from that viewpoint. So the difference is, again, one of the very typical differences, at least, is some unusual excitations are present at the boundary. So as I say, the other thing about it, there's a kind of rigidity to the thing. So topological matter, as I say, is classified by these whole numbers, so they can't change continuously. And it makes the much more immune to dirt or disorder. For example, if I want to make regular semiconductor technology, I have to make silicon wafers. I have to go in a clean room where everyone is kind of suited up in these white suits and everything that doesn't allow interchange between them and the sample. That's not to protect the personnel against anything nasty in the room. It's to protect the beautiful silicon wafers against anything nasty coming from the people. But you have to be very, very careful, because one speck of dirt will ruin the whole chip, the whole wafer. Now, the topological matter properties, if you're trying to use something based on the topological properties, you've got to do, since you can't change from 0 to 1 by a single speck of dirt, you've got to do something much more violent to change it. So it's much more rigid and stable against, it's much more forgiving to impurities and things, because the topology is fundamentally stable. So the classic example in mathematics is the classification, the original topology, due to, in fact, Carl Friedrich Gauss, who I saw was on a poster outside, which I also have on my talk, it turns out, is the classification of closed surfaces by the genus, or the number of holes. And so a sphere has 0 holes in it, and the usual example is the donut or the bagel, depending on which country you're in, I guess, is a torus, which has 1 hole in it. And counting holes naturally comes in whole numbers. There's no such thing as 0.3 of a hole, right? So holes are a topological thing, and they come in whole units. And I think I'm out of, dare I touch it to move this up a little bit? It's okay. Kind of unfamiliar technology there. Okay. So the fundamental formula in topology, the origin of it is this amazing connection between geometry and topology that Gauss apparently felt was his most amazing discovery ever. He gave it a fancy Latin name, Theorema Egregiema or something like that, which basically means amazing theorem. And he discovered that if you integrate the Gaussian curvature of a sphere, which has got uniform curvature 1 over r squared, and integrate it over the area, so 4 pi r squared times 1 over r squared gives you 4 pi. Of course, that's a trivial high school formula. But what Gauss discovered, of course, was if I deform this sphere into a rugby ball or American football or into a banana or whatever, it was much more challenging to do this integral of the Gaussian curvature over the surface. But I guess you could give this to your students, and you could test them and have them come back, and you know the answer is going to be 4 pi anyway, and they're going to work very hard to find it. And of course, they'll only... So this was a remarkable formula, and as I say... okay. We're going to get this thing up. Oh, it does move. I guess I can... Okay, I'm learning the touch screen. A little bit more. Anyway, I can move it that way. Yeah. So again, we have this famous business about bagels turning into coffee cups and etc. Okay, so you do these integrals, you get 4 pi 0 minus 4 pi minus 8 pi, etc. Okay. So how's this got to do with entanglement? So the entanglement you can explain from this more modern viewpoint. At least we can look at various measures of entanglement. One measure of entanglement is the Schmidt decomposition. And that means I can take a quantum system and I can basically kind of divide it into two. I can use a basis set of quantum states that describe the left-hand side and a basis of quantum states that describe the right-hand side. And I can write the state as a sum over, as an expansion in products of states of one side and the other side. And the most trivial state you can write down is a state with trivial entanglement, which means that the quantum state of the system is just a direct product of a state on the left and a state on the right. That means I can do any kind of measurement I want which is measuring degrees of freedom that live in the left, and they're not going to have any effect whatsoever on the state of the right-hand side. So that's what we mean by unentangled. Now, if I have so that means an unentangled state, I could just, in principle, separate the thing into two parts and just move these two things away from each other, and nothing changes. There's no kind of interaction of any kind between the two halves. On the other hand, a state with non-trivial entanglement, one of these topological states, which typically has some kind of edge state around the edges, the edge state is really there because there is a fundamental entanglement across the system that if I try to break it it doesn't factorize. And so if I try to pull this thing apart into halves, I'll find that this entanglement persists as I try to pull it apart. And when it eventually snaps, a bit like a bar magnet, when you break a bar magnet into two halves, I can't separate the north and south pole. That's actually nothing to do, that's a long-range order property, but this is the entanglement property. The entanglement property means that once it breaks, I get the edge state, the leftover bits of the entanglement that was broken here, the broken ends of the entanglement form the new edge states that live on the boundaries of the separated piece. So I couldn't do a very simple clean cut. And so I say topologically trivial states of matter could principally be assembled by just bringing the constituent atoms together with all the electrons remaining bound during the process of bringing them together. But if you're creating a non-trivial state of matter that's topologically non-trivial, at some point as I'm bringing these atoms together, there is some kind of transition where the electron states, the bound states which are bound to the various atoms, they get liberated and they move around and they rejoin in a non-trivial way. So there's something that has to happen along the way. And actually this is, so for example, the recent developments in band theory of band topological insulators, which are now sometimes called symmetry-protected topological states, is their interesting edge states. And of course, a lot of this stuff, when you go back, was actually found quite early without understanding it was all part of a big picture. Even if I look at Berry curvature, which Berry managed to realize was an important feature of adiabatic quantum mechanics, go back before that, you actually find Berry curvature or Berry phase type physics, but in little special cases, someone noticed that, for example, the sodium-3, Longuet-Higgins found that the sodium-3 molecule had some John Taylor effects we wanted to make it distort, but there were some interesting things when the distortion moved around, you got a -1 for. So there are lots of special cases, but no one put this stuff together and saw a general principle. So in fact, if you go back as far as 1939, essentially, it's not quite a topological insulator of the current variety, but it's a symmetry-protected structure. Shockley was looking at a one-dimensional toy model, and as I say, toy models have turned out to be incredibly important. Toy models used to be dismissed either as homework problems you did on the way that kids did before they became real physicists, which was real men at the time, I suppose, as opposed to. But they would, this was some kind of puny theorist would be playing with these toy models, and that was a step on the way. It turns out that toy models are incredibly useful for looking at general principles. Great, very virtuous ab initio calculations to get all the details and energies right. Those are good too, but they didn't discover the topological insulators, although the stuff was sitting under their noses, because it's all a question of imagination. If you don't know something amazing is out there to be found, it typically doesn't get found until someone is kicking a rock around and stumbles over it. And then, of course, you say, of course it's there. But the discoveries always tend to be an issue. We don't find something because we can't imagine that we would find such a thing. But anyway, with the toy models, that makes it somewhat easier to do. And this is a calculation that Shockley did back in, oops. Go back to it. Shockley did in that one, right? Shockley did in 1939, and since they didn't have electronic computers, I believe this must have been done with a room full of people, probably ladies at that time, working passing with a handheld with machine calculators, and they calculate something and pass it on to the next person. So basically, human version of chips, of transistor arrays or something. But they managed to diagonalize this problem of 8 or 9 potential with something like 8 or 9 electrons, or atoms rather, for a simple 1D model. And this is actually what they found for the band structure of the thing. When the atoms are widely separated, so basically you've got a single little bound state, little exponentially localized bound state sitting in the bottom of each of these wells. As you bring them together, they broaden. And you see what happens when there's a special point at which the gap seems to collapse, and then it reopens, and it leaves behind a pair of states in the middle of the gap. And this is actually an example of a symmetry-protected state. The protective symmetry is not the time reversal invariance, but spatial inversion, it turns out. And what's actually going on there is that when the widely separated atoms, you just have the lowest orbital of these toy atoms is an s orbital, which is just an inversion symmetry even case, because we don't have angular momentum, just inversion symmetry in 1D. The second level up is a p orbital, or an odd orbital. And when they're widely separated, the band, of course, extends from Bloch vector, or Bloch number, I suppose, minus pi to pi, or divided by a, I suppose, the lattice spacing. But the states at the 2 points on the band which have inversion symmetry are they're both even for the lowest band and both odd for the upper band. What actually happens as you bring these things together, the states of opposite parity can cross each other. There's no symmetry. They have opposite symmetry, so they can go through each other at the thing. And as you bring them close together, they become degenerate, and then it opens up that the plus at the zone boundary becomes higher than the negative parity state. And since the bands can mix away from that, the two bands separate again. So you get this special feature of a Dirac-like point at the zone boundary, which closes and then reopens. And the bands are now topologically non-trivial, because out of free atoms you could never get, which are widely separated, you'd never get a band which has opposite parity symmetries at the zone center and the zone kinds. That's something that's impossible. So so that's the topological non-trivial nature of that band. And it's interesting that we saw it, or it was seen, Shockley saw it. Of course, he didn't really know what he didn't realize this was a fundamental symmetry principle. I mean, he may have realized there was a mixing of the S and the P bands crossing. And the other thing you actually see in this, which is kind of interesting, you see there are two states which are left in the mid-gap, and these are actually edge states. So it's a very typical thing. There's something interesting happening at the edge. Here, the two edges of this sample, which are now different from the vacuum region, because they have these funny bands in them, have edge states. And suppose I have 1 electron per atom. That means I have to add the number of states I have to occupy exactly the number of atoms. But now there's 2 states. So if I have exactly 1 electron per atom, I'm going to have to put the chemical potential or the Fermi energy exactly between these 2 very highly degenerate states that become extremely degenerate because they're exponentially localized at each end of the chain. So it's actually very unlikely to get the chemical potential in there. So if a chemical potential is below those two things, I've got one electron too little. And where is that charge? You actually have charge. We're missing half an electron at each end of the chain. And if the chemical potential is above the mid-gap state, I've got one extra electron, half of which is at one end and half of which is the other end. So actually, one of these other things one sees, like fractionalization of charge, is actually also exhibited in this 1939 model. So kind of interesting. And actually, fractionalization of charge, at least in the quantum Hall effect, the fractional quantum Hall effect, is another typical thing that's been seen in topologically non-trivial materials. And of course, in empty space, the electron, since quarks are bound by the gluons, we only have charge E that kind of flow around. But inside a material, suppose I have a density wave type state where the electrons repel each other on some lattice. So they like to, a short range repulsion between the electrons may stabilize a state where there's one electron on every second site. Oops. And suppose I remove one electron. You can see that if the energy principle only requires me to avoid having electrons on adjacent sites, I can rearrange things, and I clearly removed one electron, so this had a local charge deficit of -1, but I can split it up into two objects, which are charge deficits of -1/2. And so that's a typical example of fractionalization in an unusual state of matter that we see. Okay, so spin systems. So one of these discoveries is one of the things which I found back in 1981 is to do with unexpected properties of spin systems. Now, in heavy atoms, a group of electrons in a group of orbitals, atomic orbitals come locked together, like in the d orbitals or f orbital. The Hund's rule wants the electrons to lower their energy by being parallel. So we can, of course, assemble the quantum spin is really assembled out of electrons, and if it's in an insulating state, then there's an integer number of such electrons, and so we get a total spin. Since the electron spin is 1/2, 2s electrons give me a spin s. And the spin of the electron in a magnetic object, the spin of a group of electrons in a magnetic orbital is s, where 2s is a whole number. Now, before 1980, most of the states that people understood, at least, were actually what we'd now call essentially unentangled states. So these were the basic model for magnetism was the magnet was viewed as like a little top, or the spin is a little unit of angular momentum, and the two kind of classical cases are the ferromagnet and the antiferromagnet, where the spins actually want to line up in the same direction. And this Heisenberg model, when it orders, there's a broken symmetry where the system picks out an arbitrary direction to localize, to point the spin direction in. And in the antiferromagnet, spins on neighboring sites are antiparallel to each other, but the system has still picked out a particular axis to align the spins parallel or anti-parallel to. Well, this kind of state is still a complete superposition, because in this toy model state, every spin is independently orientated along its axis, and I chop the thing in half, it'll just fall apart into two things. Now, when you look at the things, there's some corrections. The antiferromagnet has some zero-point motion of the collective modes, which gives rise to a little bit of entanglement. But these are fundamentally, they're not topologically distinct from a totally unentangled state. So the toy model state for these things, this is called the Niel state, and this is the ferromagnet, are completely unentangled states. And of course, things do interact, so they get a little bit of non-topological entanglement. So the surprise was I found out that the spin 1 chain, apparently a kind of one of these toy models that people had looked at as a kind of homework problem before treating real magnets, actually behave completely differently from the expected behavior. And what actually emerged from all of that is that the actual state of a spin 1 chain, it forms an entangled state where instead of having this antiferromagnet, instead of having the spins alternately unentangled up, down spins, they kind of break up, and each spin kind of fractionalizes into 2 bits, joins hands with its neighbors. So if I try to cut it at any point, I do have an entangled state, and I have, at the end of the system, I get left over, if you're joining up people, everyone holding hands, the 2 people at the end of the either chain, they have one hand flapping around with no one to hold on to. And that's this half of a spin, and if I cut the thing down the middle, I get left with half spins at the cut too. So this was a kind of state. It's now called a quantum spin liquid state. It hadn't been dreamt of because people thought that magnets always did something like the top picture. Okay. And in fact, this was, I'll come to the history of this thing. This thing was, I didn't think it was so outlandish. I did write in the paper it was an unexpected conclusion. But this thing was rejected at least 3 times. Referee's report said things like, in fundamental contradiction to basic principles of physics like renormalizability and continuity, all kinds of, pedantic kind of stuff like that. This because basically people already decided what these things did, and this was just a paradigm shift. And of course, it's right that if you propose something that's different from what people believe, they give it a hard time. Because otherwise, all these Einstein were wrong people would be kind of publishing right, left, and center, rather than sending the stuff to me in my email every day. But anyway, this was a kind of, amazingly, this was a sort of heretical notion, apparently. So the basic thing was in spin wave theory, which is valid in these magnetically ordered states, spins fluctuate relative to some fixed orientation axis that occurred by broken symmetry. And it's sort of, the usual picture had just like harmonic fluctuations. So the spins never actually fluctuate a large angle. So they never do anything like do a full 2-pi rotation that would kind of measure what their spin was quantum mechanically. And the view was that the spin quantum number S, when in the spin wave theory, it just enters as a kind of a number. And it plays really the role of h bar. So 1 over S. If S goes to infinity, it's classical. So 1 over S is kind of like h bar. So it was sort of a number that seems to be a real number, and it's just a measure of how quantum it is or not, right? How large the angle you're allowed to fluctuate away from the 0-point motion takes you away from the ordered state. So the order parameter strength goes down with a spin, but it was viewed it was a continuous function of 2s, which is where this comment about basic principles of continuity came from, right? So there was no indication that the value of 2s as an integer was a topological number, which of course it is. Okay. And in fact, a key thing which was known at that time was the Mermin-Wagner theorem had already ruled out long-range order with at any finite temperature with a continuous broken symmetry, and that was actually the puzzle that the other part of work of this Nobel Prize got. Kosterlitz and Thouless resolved the issue of how you could have experimentally a quite observable, obvious kind of phase transition happening in superfluid films when the mathematical Mermin-Wagner theorem said it was not possible to have a transition. Again, when exact mathematics enters, it's very exact mathematical results are very treacherous because people who prove them, they believe. Of course, there's nothing wrong with the result. And they kind of prove from line A to line Z, you can, all the way through. It's absolutely rigorous. But what's usually wrong about these things is the interpretation of the implications of those results. So Kosterlitz and Thouless solved this puzzle in 2D. And the Mermin-Wagner theorem also applies in 1 dimension with the proviso it doesn't apply to ferromagnets where there's a kind of angular momentum conservation law for the order parameter. But if the system has 0-point fluctuations, which is the quantum mechanical analog of finite temperature, then in 1 dimension, in the ground state, you can't have a long-range order of any conserved order parameter. So the antiferromagnet has this feature that the quantum fluctuations, in principle, was known destroyed true long-range order. So there should have been people should have been more open to realizing that spin wave theory really had nothing to do with one-dimensional systems. But again, exact mathematics comes in here and played an interesting role, because way back in 1931, again, as a toy model, Hans Bethe studied a chain of atoms, and he made the assumption that the energy kept you to 1 electron per atom, so it was a one-dimensional chain of matter. He called it one-dimensional metal, and it's in German, in Zeitschrift für Physik. Anyway, he solved this problem by accident. He came up with a guessed wave function, which remarkably turned out to be a correct solution for this particular model. He actually didn't realize how special it was, because he thought the paper actually promises, in the next number of this paper, number 2 of this series will solve this we'll use the same method in 3 dimensions to solve the problem. Of course, it didn't, right? And it took about 50 years to understand why Bethe's solution worked, and it's got some very deep and powerful mathematics that's very, very special to the model. Okay. Then, of course, Hans Bethe went on to probably more important things, to find out how the fusion in the sun works and stuff like that. And in fact, he was also later did another important thing, which was he was David Thouless's advisor at Cornell. But anyway, so there was this exact but very inscrutable solution. And the thing was, I'm not sure if I say it in one of these slides, it looks almost the same as spin wave theory. Let's see if the next slide, I probably missed out a slide which says that. The solution of Bethe's thing, it looks exactly like the predictions for spin wave theory, except the spin wave velocities for the spin half thing's off by a factor of π/2, and that's okay, some quantum correction. And of course, looked at in a bit more detail, people should have realized that if you actually calculate the specific heat, now the Bethe solution allowed you to compute the energies, but at that time there was no known way to extract the correlation functions or any kind of measurable things. So you had a method which gave you energies, and out of that you could do thermodynamics. But the other stuff was missing, and it took another 20 years before it was discovered how to extract such things. So people thought the Bethe solution was spin waves, because it had the same kind of, analytically the same expression for the lowest energy excitation, just by a small factor wrong, and it turned out to have no relation of any kind to spin wave theory. But this gave people the belief that, okay, they knew that spin wave theory couldn't properly work absolutely because of the Mermin-Wagner theorem, but they thought, okay, the Bethe solution showed it was slightly modified to have power law fall off of correlations rather than long-range order, but it was morally correct, and that was a complete mistake. So basically, the people who understood the mathematics of Bethe's solution didn't understand anything about physics, apart from Bethe himself, and he didn't understand the mathematics of his solution. It became, comes into quantum groups, basically. It's a very abstract thing. And of course, the physicists who worked on magnetism couldn't understand the mathematics, so no one got together to kind of say, no, this is not the right interpretation of the result. But anyway, it's kind of interesting piece of sociology. But around about the 1970s, there was another piece of work left over from the 30s, the Jordan-Wigner transformation, that allows you to map a system of spin-a-half system into fermions. So the spin-up state maps into the occupied state, and the spin-down state into the empty state, or vice versa. I guess I've written it back to front there. And to make them anti-commute at different sites, there's something called a string factor in front, which is the Jordan-Wigner factor. But this gave you a mapping from the spin system to fermions, and that opened up a new way to analyze this problem, to actually be able to compute things physically. So the problem was actually converted into a spin half chain, converted into a spinless fermion system, and in zero magnetic field, the fermion system is half filled, which means that not 2kF, but 4kF is a Bragg vector. So in zero magnetic field, 4kF is a Bragg vector, and Luther and Peschel converted this to a field theory. And the interesting thing was that if you made an XY model by switching off the SZ-SZ coupling, it's a free fermion system that you can solve completely. So this opened up a way to actually do some calculations for this spin half chain. And actually what got missed out was, turned out to be the ingredient that made things more meaningful, is that because of umklapp processes, because 4kF is, momentum was only conserved modulo 4kF in this, when you're exactly at half filling, you could actually have a process where 2 particles from the left scatter from 2 particles to the right. And initially that was omitted by Luther and Peschel, who'd worked on umklapp processes in the electron gas with spin, because initially you might write, you take 2 right electron operators, psi dagger right. Pauli principle kills that. They forgot there's actually a subleading term when you put in the gradient into it. So this thing got missed in the original formulation of stuff. And around that time, I worked on a method for analyzing one-dimensional systems, Fermi systems, and found out there was a topological aspect to it, kind of winding numbers and things which hadn't really been emphasized in the previous work. And that gave one a way to actually start to calculate things by extract from the spectrum of the beta ansatz models what a parameter that controlled their correlate. They had power law correlation exponents and things. But anyway, once I calculated this thing, it became clearly obvious that the missing ingredient, what happened at the transition from an easy plane to easy axis, was a Kosterlitz-Thouless process actually driven by this umklapp. And in fact, it's a not quite standard Kosterlitz-Thouless process, but I'll come to, because in the spin half system, it required, there was a quantum mechanics is different from classical mechanics, classical statistical mechanics. In the Kosterlitz-Thouless process, which is really a classical statistical mechanic thing, they look at the effect of vortices in a fluid. And the parameter that controls vortices is a fugacity, which is just e to the exponential of the chemical potential. It's a real positive number. But in quantum mechanics, when you map 2 dimensions into 1 + 1 space-time dimension, numbers which are real numbers, Boltzmann factors in classical mechanics, become, in general, complex numbers in quantum mechanics. And if there's time reversal invariance, they become real numbers. But they could be positive or negative. And it turns out the fundamental thing that's happening in the spin half system was a interference process that kills the single vortex. But once this was done, once one looked at this, one could see that you could actually turn these spin systems analyze them from the point of view of what we call Luttinger liquid theory, a kind of one-dimensional fluid approach. And so that turned the thing from being just a special one-dimensional spin half system. It allowed one to formulate the system for general spin. Before, it looked like Beta's solution was special to spin a half, although it wasn't. And the Luther-Peschel treatment was special to spin a half. But putting it in a more general context, that immediately showed up that the Kosterlitz-Thouless process was going on. So the tunneling, the vortex tunneling events that happen. So this would be the space-time picture of a tunneling process which takes you from an easy plane system where the spins are like little compass needles in the plane. So they have a kind of winding number as I go around. If a spin lies in the plane, I go along the chain, it winds a certain number of multiples of 2 pi if it's got periodic boundary conditions. And the transition in the Kosterlitz-Thouless system is a vortex unbinding process where there's the spins. If you go around the spins, you find, if you walk around the system and see how the spins are rotating, you'll find they've rotated through a 2 pi if I go around the closed path. Well, this picture in quantum mechanics, this is a tunneling process at some point where the winding number, if the spins are all essentially anti-parallel to their neighbors, then the winding number of the spin of the planar spin going around a closed loop is conserved. But in the center of the vortex, you can see there's two neighboring spins are parallel to each other. The order parameter broke down at that point. So this is actually a tunneling process between 2 different topological configurations. And the key thing here is that if I look at this more closely, And you can see the tunneling process happens on a single bond between two spins. If I move the tunneling center to the next bond, the only change in the two things is that one spin that rotated 180 degrees to the left now rotates 180 degrees to the right, which is equivalent to one spin rotating 360 degrees. And if it's a half-integer spin, you pick up a -1 phase factor for that. While if it's an integer spin, you don't. So it turned out that the behavior that Luther and Peschel, the people found for the spin half chain, was the critical point exactly when it went from easy plane to easy axis, couldn't be the case for the spin one chain. The spin half chain has a transition at the Heisenberg point where it goes from an easy plane. The spins want to lie in the plane. Here they want to lie along the z-axis, and here they can point anywhere. There had to be some place in the middle, which turned out to be this topological state that I showed. And this was, but basically, without this new kind of looking at it, you wouldn't have guessed this in any way. And so it comes out very naturally from considering, in this case, topological structures of this whole thing. So this turned out to be, at the time it wasn't known, but now this is being viewed, at least by Xiaogan Wen made a big classification. This is somehow the hydrogen atom of topological matter, the most simplest of all the cases of the classification. So it's somehow amazing thing, and there was lots of various topological stuff that happened along the way. It turns out, at the same time, this difference between two ways of quantum mechanics affecting the antiferromagnet was very mysterious. At the time, when I was doing this, no one in condensed matter had ever really done anything with Lagrangians. The field theorists, the particle theorists were working with Lagrangians, and the condensed matter people working with Hamiltonians. And it turns out, of course, the topological terms can show up in a Lagrangian as something that's linear in the time derivative. This is the topological term that shows up in this spin chain that controls the difference between integer and half integer. And it's got one derivative of time here. So if I form the Hamiltonian to this, it disappears. Anything that's linear in the time derivative disappears when I go from the Lagrangian to Hamiltonian. And interestingly, the pure topological matter states have Lagrangians which don't have this model has an energy term here. The pure topological field theories only have terms like that. And in fact, one time I heard Tony Z giving interesting sort of talks about abelian multi-component Chern-Simons theories for the quantum Hall effect, et cetera, et cetera. Very beautiful stuff for the topologically ordered state, which has like zero energy. And one of the audience put their hand up and said, "Excuse me, what's the Hamiltonian?" And of course, Tony wasn't used to that, but he thought a bit. He said, zero, of course. And you should have seen the face of the experimentalist. All his worst prejudices about theorists were confirmed. So anyway, topological pieces have this interesting feature. They don't show up in the Hamiltonian, and et cetera. This model has both a topological and non-topological piece. And later on, this very beautiful kind of local model for this state was developed, the one I showed the picture of, by Affleck, Kennedy, Liebman, Tasaki, which made a modified state, which is not the state of the regular antiferromagnet, but turns out to be the exact ground state of a modified toy model. Again, showing the importance of toy models. This is a model state where I add some extra terms to the standard Hamiltonian, which you wouldn't expect physically, but actually make it much more tractable and has a nice, very clean ground state, but is in the same kind of topological class as the physical model. Okay? And this one I showed the picture of where the spin actually can be fractionalized and into two spin 1/2s, and they join up. And if I do a cut down the middle and look at the so-called Schmidt spectrum, I'll find there's a single spin half doublet, which is a double state of the Schmidt spectrum here. And it turns out, of course, for the general problem, there'll be many more states in the entanglement spectrum above some kind of gap, but every state in the Schmidt spectrum of the topological state is doubly degenerate. So there's a kind of complete by looking at the entanglement, you can immediately see the difference from a standard state. And again, it has these spins at the end. In the AKLT model state, the spin is completely localized at the end. In the more physical generic model, the spin is exponentially localized. It's not completely on the last stage, but it's still, when I make the thing long enough, then the two spins are completely separated on the two ends of the system. Okay, so let's move on. And in fact, this AKLT state got put in my diploma I got for the Nobel Prize. The artist, you get a everyone gets an individual watercolor on their diploma, and they chosen to put the AKLT state on mine as some kind of snake swimming in the space-time background or something. Okay, so the second surprise that happened was the quantum Hall effect in 1980, a little bit before, probably a few months before I found this thing with the spin chain. And of course, there was no obvious connection of any kind. And there the thing showed up first that you do this measurement, and von Klitzing discovered that he put a sample in a field. He put a sample held at constant current through a constant current generator, and he put it in a magnet and switched on the magnet. And it's lucky he did it that way, because every time he switched it on, the digital voltmeter reading the whole voltage measured from side to side of this sample gave exactly the same number to about 4 or 5 at least significant figures. And of course, he thought he had a dud voltmeter here. Because you shouldn't, you can never get that as a result. And of course, if he'd actually done the experiment the other way, by putting the thing with the field switched on and ramping the current up, the current would have never stopped at this. He'd have never got the same voltage out of it. So the amazing thing was he got this thing, and this is a sample, one kind of sample. This is probably what the fractional Hall effect sample, I don't know what von Klitzing sample looked like, but it vaguely looks like a graduate student did the soldering on the thing. But I imagine not, because it's very small, I suppose. But you can see that you can measure such a precise thing in a very forgiving way with this kind of sample here, right? And of course, this is electrons in a magnetic field. So the electrons are going around in little orbits, and so a Landau level is a sort of little sort of circular-like orbit around the guiding center, and the two-dimensional system traps the electrons, so the only degree of freedom is where the guiding center is. And if the magnetic field is uniform, then the energy is very flat. And so it's almost like an atomic diagram, except instead of sp, df orbitals, etc., there's the number of orbitals in each of these Landau levels is macroscopic. There's one for every quantum of magnetic flux through the system. So there's a huge macroscopic degeneracy. And naively, you could understand von Klitzing's result with the most naive way by saying, well, if I happen to have this perfect system, which was these perfectly flat bands, and I tune the magnetic field, since the number of electrons is fixed, as I tune the magnetic field, there'll be one field where I exactly get the number of states in level right to fill this thing. And then in principle, if I did the calculations there's a gap in the system, and I should get exactly the experimental result. But on the other hand, this seems to require the field to be made exactly perfectly right, and everything to be absolutely clean and all that kind of stuff. And that's the opposite of von Klitzing's fact that the thing was so stable. And of course, it turns out, Bert Halperin noted that these quantum Hall systems, they have the electrons are going around in the bulk in, say, this, I've drawn them going around anti-clockwise, but if they bounce off the surface, they will actually, I guess they're going around clockwise, and if they bounce off the surface, there'll be a kind of skipping orbit state in the anti-clockwise direction around the edge. And this turns out to be the clue that this thing is actually a topological effect. So you absolutely have to have edge states, which turns out to be the typical feature of topological systems. And that means it bends these levels up at the edge. And so the Fermi level gets pinned somewhere in the at this point in this toy model. And this clean toy model doesn't need any fine-tuning to get here right. Provided the Fermi level is anywhere pinned in this region, the edge between the gap, then you'll get the von Klitzing result. Now, of course, the real system is much dirtier than that. And Thouless, I shared the prize with Thouless. He shared it in two things. He shared it with Koslitz for the Koslitz-Thouless effect. And this other work is topological quantum stuff. And his contribution there was, he noticed, of course, the physically motivated problem would be some messy random potential inside the thing. And the original work on this thing focused on localization theory, and which is a very intractable kind of problem. Well, Thouless actually, again, had an idea to use a toy model approach, and he looked at a simple periodic potential rather than a random potential to kind of give you some splitting of some spreading of the Landau levels to widen them. And so he looked at this problem, and I guess I'm not sure I'll show the slide of the Hofstadter thing, which I probably don't. I took it out for this. The simple periodic potential in the bulk is absolutely not related to the physical problem, but it's tractable. And they found this amazing formula. They were trying to understand the Hofstadter problem is the problem of a random potential, and it was known what the spectrum was like. And basically, whenever the chemical potential is in a gap, there was some number which is an integer number, which is analogous to the number of filled Landau levels in the simple case I showed, but it wasn't clear what it was. Well, they came up with they used the standard Kubo formula, and they came up with a very simple formula, which is this one down here, which basically ended up integrating some quantity over the Brillouin zone, and they saw this had to be an integer. And in fact, at that time, a mathematical physicist, Barry Simon, someone had told him about the Berry phase. He had these two pieces of different information, one that Berry had found the Berry phase, and two that Thouless and co. had found this formula. And he managed to see the connection to Chern's classification, which is basically a generalization of Gauss-Bonnet. So the Gauss-Bonnet theorem is, of course, coupling the physical curvature over kind of physical surfaces. The mathematical abstraction turns that into a much more abstract curvature over much more abstract surfaces. And of course, that's what this quantum mechanics is, but this is what was identified. So this was actually the first explicit realization of a topological formula in this business. The formula that showed at least if I had a periodic potential, then there was a topological quantized. The whole effect was topologically quantized. Okay, so at this point it was kind of everyone thought the whole effect was something to do with high magnetic fields, and in fact, in 1988, I was actually intrigued by a paper which I thought was an incorrect paper, but a paper proposing something that started off with a time reversal invariant system, a bit like today's topological insulators. At the end of the day, found something like a quantum Hall effect. So it seemed to be getting a quantum Hall effect without a magnetic field, but it didn't. But there had to be something wrong because there was no time reversal breaking in it either. So thinking that through, I actually realized that the basic thing for the Hall effect was not the magnetic field, but the breaking of the time reversal by and you could do that by some magnetic arrangement. And this turns out to be what's now called the zero field or anomalous quantum Hall effect, which for many, many years was just a kind of toy model, and it was very influential in what it led to, but actually in this last couple of years has actually been realized in China. Okay. So this was the model for the quantum Hall effect without a magnetic field. And it's a very simple model. It's something like graphene, which wasn't known at the time, so I called it monolayer graphite, because I guess Semenoff had already pointed out that a monolayer graphite was a kind of scenario for the Dirac equation. Except, so in this case, you needed to break the time reversal, because in the graphene, the Dirac points are stable, provided both inversion symmetry, spatial inversion symmetry, and time reversal are unbroken. So basically, it's a simple kind of model for graphene. It's actually spinless electrons, but with a magnetic order, a little magnetic dipole at the center pointing outwards. And the magnetic dipole pumps kind of flux in and out through the plane. So in 2 dimensions, there's no net magnetic flux through the system by putting a layer of dipoles on it. So there's no net flux through the unit cell, but different parts of the unit cell have magnetic flux through them, so you pick up phase factors. In this toy model, you go around this loop, you go around these second neighbor things, and you see there's a kind of chirality, which is one-handedness, one way if the dipole is pointing up, and the other way if the dipole is pointing down. So there's a kind of coupling between, this is an anomalous Hall effect due to a magnetic structure rather than due to magnetic flux, and then if I flip the magnetism the other way around, the Hall effect changes sign. Okay? And it turned out, so in this graphene model, if you have the standard graphene model, you find there is a bound state. If I now look at the edge of graphene, the simpler one, I should have done a picture. You can cut it in one way, which gives you a kind of zigzag edge. So if I cut it so the free edge is this kind of zigzag here, as opposed to the other one, it's called armchair. You find the projection of the 2 Dirac points onto the surface band occur at 2 different points, and there's a surface bound state connecting the 2, which is actually very much like which was found much more recently in the 3D topological insulators, where they on the surface have something called Fermi arcs connecting the images of the points. Well, the graphene has that too. Oops. And so when you break the symmetry, if you break inversion symmetry or time reversal symmetry, you open up a gap. But you can see that when I break any symmetry, this point has to remain attached to some place that used to be the touching point in the Dirac place. And there's 4 choices. This side can choose to go to the upper band or lower band, and that side can choose to go to the upper lower band. So in the material that Semenoff studied, which was actually breaking the spatial inversion, all you get is a boring insulator. You get a massive Dirac equation. Oops. Okay, my control's going the wrong way. There. You get a massive Dirac equation, and you either get a bound state which is connected to the conduction band or the valence band. So you can put the Fermi level in between, and I get a boring insulator. But if I break the time reversal, they couple the other way, so there's always a kind of connection between the 2. And that's necessary, because if I start to put a magnetic field on this thing, I have to actually pump electrons from the valence band to the conduction band. So there has to be a kind of pipe connecting the 2, and that's what this edge state does. And you can see it's going one way around the edge. The slope is to the right here, which means that's going to the right on the edge, and that's going to the left on the edge. So actually, this is actually very recently. This was not experimentally realized for many, many years, but very recently, actually, this is perhaps the Chinese version of an internal Chinese Nobel Prize or something, because it's a big prize that Shikan Xue got, for various things. But they mentioned the quantum anomalous Hall effect, and this ended up being made out of I'll come to that, the topological insulators, and sticking some magnetic material, depositing it on the surface of the magnetic insulator. And then you have to put a very small magnetic field, as you do in the anomalous Hall effect, which aligns the magnetism, but it's got nothing to do with the flux. It's not driving things. You need a small magnetic field to switch the magnetism, and you can see that you see a hysteresis effect. You get a jump for the quantized value here. Now, these quantized values they don't seem to be universal, because this is actually a measurement of rho xx and sigma xx, which is rho xx over rho xy squared plus rho xy squared. So you have to convert from resistivity to conductivity if there's a finite dissipation in the system. But when plotted, they found again that these things all scale. The values of the plateaus scale, at least in the region of gate voltage, to precisely the expected quantization. The blue curve, I think, is sigma xy, and it goes up to exactly this quantized value. So you have a switchable quantum Hall effect. Instead of the magnetic field coming, a small magnetic field is used to kind of trigger the magnetism to go either up or down, and you can switch it from going to the right or the left. And of course, the dream, one of the technological dreams of this thing, is you separated the motion. It's like a divided highway. On one side of the sample, all the currents are moving in one way, and it's moving in the other way on the other side. So you get a much more ordered. By separating the traffic, you can get your traffic to flow much better than you can by no rule of the road. Like, I'm not sure which country. Some countries have that kind of. Maybe not legally, but practically have this sort of chicken-type driving, right? But this keeps the traffic apart, and there you are. And in fact, there's a lot of other interesting things you can do with this now it's been made. For example, before there's a lot of talk about putting superconductors in contact with quantum Hall devices, and there's all sorts of interesting things that happen when you add superconducting non-conservation of electron or whatever to the system. And of course, you can't stick your superconductor into a 20 Tesla magnetic field, because with the magnetic field way of doing it, they're completely incompatible. But now, if it's surface magnetism that's doing the effect, you can stick the superconductor on top without having a field to ruin your superconductivity. So it's kind of very interesting. I guess I'm probably going to wrap up. But it turned out this general principle of this toy model actually turned out to be transferable from electrons to photons. So these topological edge states, initially, you'd have thought there's no connection between charged electrons in a high magnetic field and doing Landau orbits and what photons can do. But once you realize it was actually some aspects of the quantum Hall effect, for example, for the integer one, filling things up with the Pauli principle don't work for photons, but the principle of the edge states is still there in the photons. And once again we realized that was possible, it took some time to convince ourselves, but eventually found an explicit model, again a triangular lattice of rods with various dielectric and Faraday effects things in them, which simulated exactly this graphene model. One actually did a calculation and proved it worked. And in fact, it's now been done, at least on the level of microwaves. You can make these systems, and then you can actually see the charge pulse of electromagnetic energy kind of moving around the edge and not being affected by putting a barrier in the way. So we've seen this topological thing. And if one can make this work on the level of optical wavelength, which people are trying to do, I mean, this would also have interesting technological aspects to it. So finally, since other people took this work a lot further, I said we kind of introduced some of the early things, but it turned out that just taking 2 copies of my toy model, which actually I did as well, but didn't do the crucial thing, was people were worrying about the spin Hall effect and asking, is there such a thing as a spin Hall effect around 2004? Big discussions about whether it was a equilibrium state or not. And you take 2 copies of this model, one for spin up and spin down, which are time reversal invariant to each other. Then you have a time reversal invariant model. And of course, it has spins going both directions. It has the up spins move one way and the down spins move the other way. So you could call this a spin Hall effect. But then the question is it topologically protected? You have these spins going, these currents going in both directions. If you put anything that doesn't conserve the spin, you'd expect them to scatter and destroy this effect. And in fact, I tried this out, but I didn't actually do the calculation. I dismissed it. I said, well, it's obviously, this is a toy model, but it's obviously not stable because we didn't know there was another invariant. And I didn't actually get around to do the calculation, but Kane and Millie actually did the work they had the same idea, and they did the calculation, and they found there was a new topology. They found the thing was protected, and it turned out to be protected by Kramer's degeneracy. So, and then out of that came a new kind of topological invariant, which no one had dreamt of before in this context. We'd only been working with the one that Fowler's had found. And out of that came the 3-dimensional. Once a new invariant was found, of course, it turned out to have a very natural 3-dimensional generalization, and this whole explosion of real systems opened up. So finally, once the formula for the 3D case was found, and I think the last paper, a paper by Fu and Kane, found a transparent formula for this, Before, this was a very complicated thing you had to work out, but they found out you could look at a band structure and just check out, this was inversion symmetry, just count the parities of the inversion symmetric points and find out if we were topological or not. That immediately made libraries of band structure calculations available just to go and check out what was topological and what was not, and people kept finding these things. So the band structure people could have found this stuff a long time ago. They just didn't even dream of the existence, and the data was already waiting there, because no one had thought to look at the surface of these materials in any detail. So anyway, this led to this tremendous thing, and in fact, I think I'll stop at that point. I suppose, let me just mention one thing. Out of the fractional quantum Hall effect, essentially the generalizations that led to these things which are now called Majorana edge modes, which were initially found theoretically at vortices in the Moore-Reed, in the half-filled Landau level quantum Hall state, and later were found on the surface of if you put a topological insulator in contact with superconductor, you'd find this where the vortices terminate. But actually, more generally, they've been found all over the place now. And this is one of the Majorana zero modes, is at least one of the things that Microsoft is pushing this as one possible mode for braiding and topologically protected computing. And there's this whole subject just kind of blossomed out. So many people started working on it. All kinds of, quite surprises started emerging. So this has really been kind of just an amazing ride to see what's come out of such early, small, apparently obscure beginnings, right? And the surprises keep growing. So as I say, I think it's a great future as we start to learn. We're starting to really learn all the kind of things you can do with quantum mechanics, and it's pretty cool. Thank you.
Maybe I start from one.
Okay.
A lot of these integer comes from Hermitian Hamiltonian.
Right.
But in real life, we may have dissipations and interactions. What if this Hamiltonian becomes non-Hermitian? How robust would these ideas be?
Good question. I mean, there've been some attempts to put put dissipation terms into and try to generalize some of these topological invariants. What's the name for the? There's a thing you can see the term which goes with the Hamiltonian to describe dissipation. There's various models for dissipation that you can put in, and people have managed to generalize some topological invariants to systems with dissipation. I suppose, most of this work is really at thinking about low temperatures, but if topological stuff is stable against impurities, I mean, it should be stable against dissipation too, in some sense. And now, these are all zero temperature effects, so they sort of require you to have a gap in the system. So, what actually happens at finite temperature and how stable these things are is still an open question. Yeah, but there's people working on this. Yeah.
Yes.
About the quantum entanglement, one of the frequently encountered questions is that it may appear that one can transmit information instantly. For example, if you have two electrons or two photons, they're entangled, and then now you let it go to 1 light year apart, and then you measure one using an arbitrary axis, and then you measure certain result, and that would imply maybe 1 light years apart, and the other side, they may get a certain expected result. So this is, a couple of. So what's your view on that?
It turns out that when careful analysis shows, it's a bit like you have your laser beam and you shine it across the surface of the moon, and the spot is moving faster than the speed of light, right? You actually can't use that. You can't use that to transmit information faster than the speed of light. So same thing with the measurement stuff with the entanglement. You can't you can't transmit it. It doesn't allow you to transmit information. So that part of Einstein's problem with it got resolved.
But even though you cannot transmit, but you can detect it in a way. You know, if you already have an agreement with the other observer on the board.
Yeah. Yeah, there's a whole issue about consistent histories and things like that. But if you analyze it, you can't actually violate any causality by doing these measurements, right?
Hi, Professor. Professor Haldane. And my question is also related to quantum entanglement, because you see, you actually share that the topological stuff has the entanglement feature, and we know in quantum entanglement now people are trying to work out the theory to measure the entanglement strength, or on the other hand, there is entanglement entropy things. Whether there is something, some similar quantity you can use to measure the topological instead of just the topological invariance. Thank you.
Well, it turned out that if you calculate this Schmidt spectrum, if you do this decomposition, it turns out to be a very useful technique because the spectrum of its analog, it's not energies, but it's essentially the relative weights of the different. You split the system up into a sum of products, and there's a unique kind of spectrum that comes out of that, which is, and that has a fingerprint in it, which detects the various kinds of topological order. And in fact, Wen has made a big study of classifying different states by whether you can. So that there's a symmetry-protected states, which means that you could make a local unitary transformation between them, but you can't do it if you want to maintain some kind of symmetry along the path. For example, the spin chain I showed, it actually you can't. There's different states of the spin 1 chain, some which have the free spins at the end and some that don't. And you can't change the topological order is protected either by, for example, inversion symmetry or time reversal symmetry. If either of those are present, you can't. So there's, and in quantum Hall edge states also require, the symmetry protecting them is actually the gauge invariance of electron conservation. So one of the interesting things for applying superconductors to the quantum Hall system is it breaks the protective symmetry of the charge conservation symmetry of the quantum Hall state. So there's the entanglement spectrum. The entanglement spectrum is a fingerprint of things, and there's a lot of analysis of classification of the states by their entanglement. Yeah. So that you can classify topological states by the spectrum of their entanglement.
I have a simple question. So it's related to the symmetry protected topological phase. So this kind of phase can be protected by any general symmetry, or just limited to the time reversal symmetry, the particle Hall symmetry, and the Cal symmetry. I mean, because they're the famous Outland-Zambarro classification, or
now there's a lot of work on so-called crystalline topological insulators. So initially, you might have not expected. I mean, time reversal is a rather clean kind of symmetry. You either have something, you need something magnetic in there to break it, right? It doesn't depend on order, on disorder, but you might not have, there's various symmetries. We've got some kind of crystal plane that has some mirror symmetry. It turns out there's some topological edge states you get if you have certain kinds of, I guess, non-symorphic space groups. And so at first sight, you'd think that would be completely ruined by dirt. But it turns out that the edge state structure, those is stable, provided the dirt preserves the symmetry on average. So there are generalizations to quite a lot of different groups, mainly with, as far as I know, non-symorphic space groups and things to do with glide planes. So there's a kind of much larger kind of extension than the initial symmetries into these symmetry-protected states.
Okay, thank you.
Yes.
I also want to ask a simple question. I want to ask something in real case for experiment. Why we get very well quantized plateau in anomalous quantum Hall effect, while it's very hard to get well quantized plateau in quantum spin Hall insulator. Thank you.
In some sense, the anomalous quantum Hall effect is much more stable in a sense because you've got this one-way transmission, right? Well, I guess one of the problems in the regular spin Hall case has been kind of difficult to get a very good bulk insulator. So there's some issue about the bulk thing, getting the bulk tuned to be an insulator to get the chemical potential properly in the gap has been a difficult thing for some of these systems. But in some sense, the anomalous Hall effect is in some sense cleaner than all these things because of this absolute one-way transmission. A little bit of magnetic stuff is going to ruin is going to mess around with the time reversal invariant case, and perhaps that's the one-way transmission around the edge is somehow topologically cleaner than the two ways in the as well in 3D topological insulators. You don't have this. You only have extinction of the perfect 180-degree backscattering of the edge state, so you'll still get some. You've got a cleaner structure on the edge, I think, of the anomalous Hall effect for this kind of one-way traffic. Yeah.
Thank you.
So maybe in the interest of time, let us have the last question. Anyone want to ask the last one? If not, let us thank Professor Haldane again. Thank you very much.